Primordial black holes have been the subject of much deliberation in the scientific community in recent years. Born at the very dawn of time, these theoretical objects could potentially be found in all corners of the universe. As well as being promising dark matter candidates, they also have the potential to alter our understanding of the cosmos in many other significant ways. But what exactly are primordial black holes, and how can we possibly detect them? Before we delve into primordial black holes, we should first understand the basics of regular black holes. One of the most common types of black hole, the stellar black hole, forms when a sufficiently massive star collapses into itself under the force of its own gravity. This forms an extremely dense point in space within an extremely compact region called the Schwarzschild radius. The gravitational pull of this object is so strong that not even light can escape once it falls past this radius, lending black holes their name. Primordial black holes, on the other hand, are named as such as they formed in the early universe, long before the stellar formation period. They formed due to the collapse of primordial overdensities left over from the inflation period, when tiny quantum fluctuations were inflated in the rapidly expanding universe to form overdense regions in the radiation-dominated period after inflation. Unlike stellar black holes, which require a mass of around 1.4 solar masses to around 150 solar masses to form, primordial black holes have a much wider range of masses theoretically, depending on their formation time and the size of the fluctuation that triggered their formation, ranging from very small to incredibly large. Since the 1970s, it has been suggested that primordial black holes could constitute some, if not all, of the dark matter we know comprises around 85% of all matter in the universe. They are a promising candidate, as their existence is a natural consequence of many inflation scenarios. Moreover, it has been concluded that a remarkably small fraction of the total density in the form of primordial black holes can account for the entire dark matter density we see today. As well as possibly providing the answer to dark matter, they could also be used to probe a great number of cosmological and astronomical discrepancies. To name but a few, they may hold the key to the unexpected relationship between the mass of a galaxy and its central black hole mass, and may even constitute the very seeds of formation for these supermassive black holes lying in the center of most galaxies, far too massive to come from mere stellar black holes. Primordial black holes could allow us to probe the physics of the universe at important epochs, such as the cosmic phase transitions and crossovers, as well as being a direct link to the era of inflation, so that we may deepen our understanding of cosmology as a whole. So, how do we go about detecting them? With the success of LIGO and Virgo gravitational wave detectors in recent years, detecting primordial black holes no longer seems out of our reach. The mass of primordial black holes is related to the frequency of induced gravitational waves. As we have previously established, stellar black holes can only occur above and below a certain mass threshold. So if we were to detect frequencies corresponding to masses below this threshold, they could very well be primordial black hole signatures. These frequencies should be well within the sensitivity of LISA, the Future Space-Based Interferometer. As well as this, recent announcements from Nanograv Pulsar Timing Array has all but proven the existence of a nanohertz gravitational wave background. The universe is speaking to us from all directions. One of the possible explanations for this background are the mergers of primordial supermassive black holes. Should this be the case, these black holes would have led to the quick formation of early galaxies, as suggested by some data from the James Webb observations. Primordial black holes are as elusive as they are fascinating, and their existence has countless implications for cosmology and astrophysics alike. As our ability to search the skies improves, so too does our chance of observing them. and perhaps one day, in the not too distant future, they'll change our understanding of the universe once and for all.